one here, but we'll start with these guys. So this week in lab, you're going to be doing experiment 2. So you want to make sure you've read over experiment 2. The quiz this week will be over experiment 2. We'll talk about what you need to do for pre-lab as far as experiment 2 is concerned, because it's a little bit different than everything else. Next week, we're going to be doing experiment 3, and experiment 3 isn't hard. There's just a lot of pieces to it, okay? Read it over very carefully so that you are certain that you are prepared for it when you come to lab next week. Read it over before you come to lab lecture, so you're aware of what you're going to be doing in lab. Also, you use tons of glassware next week, like practically your whole drawer. So make sure all the glassware in your drawer is clean so that you're ready to go next week and you're not having to clean anything in between. Your samples from experiment 1 should be dry now that you can transfer those to vials. So make sure all glassware, beakers, everything are clean. And then next week your first report is due in lab. So we will be taking your experiment 1 report next week, taking your notebooks from you in lab next week. Other announcements that have occurred from this past week. Make sure when you're using the melt temps, turn off the thermometers. Make sure that, especially thermometers, if you're the last person using it, melt temps even in between people so that they'll cool down for everybody. Make sure you clean your hood and work area before leaving lab, whether in open lab or in your regular lab section, but make sure you've cleaned up everything. I spent a lot of time on Friday cleaning up melt temp areas, cleaning up balances, things like that. So you guys need to do that before. Make sure your common equipment gets back in the common equipment drawer. So thermometer adapter, vacuum trap. If you come to lab this week and you've been pink slipped, it's most likely because you have someone's common equipment in your own drawer, or you put common equipment in your own drawer. So make sure that gets back into the right spot. Make sure no water in the organic waste containers, otherwise you'll have to separate out those containers with your small sub-funnels to get the organic waste from the aqueous waste. So make sure no aqueous waste, or no water, no aqueous anything in the organic waste containers. Clean up melt temp areas and put your samples away. I've already had to take a few from melt temp areas. If they get picked up, they'll most likely get dumped, especially if they don't have their name on them or any identifying marks on them. So make sure you clean up the melt temp areas and put your samples back in your lab drawer. Don't skip class or workshop to go to open lab. You need to go to both of those. So don't try and do that in order to get into open lab to get melting point ranges done. If there's a real problem, come talk to us. Talk to your lab instructor, we'll figure out something, but don't be skipping class or workshop for open lab. And then for early morning lab people, Phelps is open at about 7 in the morning for cold breakfast, so make sure you eat before you come to lab so that you're not feeling weary and not so well come middle of the lab each morning, okay? All right, so today we're going to talk about experiment 2, which is a little bit different than any other experiment you're going to do. We call what you're doing this week called a dry lab. You're not going to actually use any chemicals in any way. But we're going to look at different types of models. And so first, it's important, why are we even doing this? Why would we use models? How can they be useful for you doing organic chemistry? So first thing, just for visualizing molecules and seeing molecules in 3D, anything we're talking about, you can't see just in the air or in the seat, see the individual molecules or in the floor, wherever. So they're really helpful for visualizing what is actually happening in the space that you can't see. And sometimes it's in 2D and sometimes in 3D. Number 2, to help understand things that you're discussing, especially right now, you guys, most of you have started discussing different conformations of molecules, what conformations they like best versus others. So it helps for to understand conformations and energy barriers. So for example, most of you have now seen Newman projections. So if we draw something like this, what Newman projection is that? It's staggered or anti, right? Is this an energy minimum or energy maximum? Energy minimum. So this is a model to help you look and better understand why a compound is going to be at a minimum in this conformation. So how about this guy? What's that one? Eclipse. So is that a maximum or a minimum? And then this guy. What's that guy? Staggered, or more specifically, because we've got the methyl groups together, that's the gauche conformation, right? And so is that an energy minimum or maximum? Remember, Baba? Min or max? It's a minimum, right? It's not the absolute minimum, but it is a minimum. And so these Newman projections help you better understand what's going on with energy barriers. Another tool for why we use models is it helps you because you can predict things by using the models too. And you'll do some of that in this week's experiment. So the two types of models that we're going to use physical models and we're going to use computer models. So you're going to spend part of your lab period using physical models, part of your lab period using the computer models. And there's reasons to use both. There's cases where it's a good idea to use both of them. So with the physical models, some of the strengths include that they're tangible. You can actually hold them in your hand and manipulate them in your hand. It's easy to see in 3D with them. Because they are 3 dimensions as you're moving them around. And expensive ones are more true to scale. I kind of put true to scale in parentheses there. As true to scale as you can make the physical models, but they are, like I said, really expensive. Now the computer models, they're not going to be tangible, they're still going to be in the computer screen. But you can, one of the strengths is you can vary what you're looking at really easily. So they're infinitely variable. And you can measure and calculate bond angles and bond lengths. You can make all other measurements as well. So you can make calculations, you can make measurements. You can optimize the geometries for specific molecules too. And you can be used to predict physical properties. Now, disadvantages for the physical models are kind of the things that make computer models have the advantage. So bond angles and lengths are an average, unless you buy the really expensive ones. And to really make it true to scale, you'd have to buy the model for the specific compound. And they're not molecule specific. Unless, again, you buy the model of that molecule, and then you're not going to be able to use that model to translate to anything else. For computer models, for the most part, for reasonably priced computer models, is they are only visual, or only can be visualized in 2D, not 3D. So what we're going to look at this week, we're not going to do, we don't have any 3D screens that you guys are going to be looking at or anything like that. So you're still is only 2D visualization. Although eventually we might get to 3D. Okay. And so just keep these in mind as you're using the models this week, how the strengths and weaknesses of both of the types of models, and try and kind of in practice realize how these apply. Now for this week, there's some things that you are going to kind of need to know going into the lab. And some of that is based on lecture, and some of it's based on things that are in your lecture textbook. So some of the core skills you're going to need. First of all, when you're looking at electron density maps, what those mean. And so you want to review McMurray Chapter 2 has electron density maps. What the different colors mean. In general, if you see something red on an electron density map, what is that telling you? It's going to be electron rich or high density in electrons, right? So we'll need to do some of this interpretation this week. If you see blue, what does that usually mean? So it's going to be electron poor, or not as much electron density. And then, kind of following the colors of the rainbow, everything in between falls in together with your red and your blue. So your green and then to yellow and orange and red progresses from low electron density to high electron density. Something else we'll need to look at is what is called saw force representations. So another way besides the Newman projections to look at compounds, we're looking at things down a certain angle of that compound. And so in the 6th edition of McMurray, it's on page 104. In the 7th edition, it's on page 93. Depending on which edition of McMurray you have. And so with the sawhorse representation, you're looking down a bond like that, okay? And then you're going to look at how things are related looking down that bond. So say we're looking at staggered conformation of ethane. This would be its sawhorse representation, okay? And so you're still, the angles of things haven't changed, the way things are arranged haven't changed. You just are now drawing in perspective of what's going on around this carbon-carbon bond instead of drawing the Newman projection, okay? And so you could even draw this as something like that, okay? And then if we looked at the eclipsed, this one gets a little bit trickier because bonds kind of fall near each other, hence things are eclipsed. And again, it'd be something more like that's the representation of the bond, okay? And you could look at, like, make these CH3s, so look at that kind of overlap. Then we're looking at what we were with those Newman projections of butane. Another thing that you're going to use, and you'll use this throughout organic, is wedges and dashes, okay? And so let's just look at methane in terms of wedges and dashes. So you've got 4 substituents on methane. It's a tetrahedral geometry. 2 of those bonds are going to lie in the plane of whatever you're drawing, okay? Then you're going to have a bond that's going out at you and a bond that's going back into the board, okay? And so to draw the out at you is the wedge. To draw the back into the board is the dash. Okay? So you'll get some practice with drawing that. And then the fun of the experiment, and some of it, you'll get plenty of practice with this, and you want to keep practicing. You'll practice in workshop, you'll practice in your note-taking on Wednesday in lecture, and then your quiz on Friday in lecture is going to have a lot to do with all of experiment 2, including drawing chair conformations and drawing them correctly, okay? And so that is how we draw cyclohexane. Or one way to show it, but it's a way to show the steric interactions that are going on with cyclohexane. And I know some of you guys got to this point in lecture today and some of you didn't, but by Friday you'll all be really good at it with all the practice you're going to have this week. So it's, if you think of in drawing these conformations, it's a series of parallel lines that you're drawing. And then you need to look at where the substituents lay off of the cyclohexane. So if you start by drawing your, and your book has some practice in here. It always takes me a little bit to get all the angles right. A little bit elongated there. But that's one representation of what actually cyclohexane looks like. So it's not, you're not going to see it laying flat in the paper. If you actually build cyclohexane, it's not going to lay down flat, okay? And the way the hydrogens come off, or substituents come off the cyclohexane, we talk about it either being in the equatorial or the axial position, okay? So axial positions are going up, equatorial positions are going out at an angle, okay? But in drawing this, what you want to keep in mind is that nothing like this we wouldn't draw as a right angle, okay? Remember, all the angles are still going to be close to 109 degrees, okay? And the other thing is sometimes you've got to kind of, to draw it, you've got to bridge over the front of the compound or the back of your cyclohexane that you're looking at. So putting a space in there means this bond lays behind this part of the ring. If you draw it where it intersects over, then it's on top of that part of the ring, okay? But all of these substituents are either axial pointing up or down, or equatorial coming out to the sides, okay? And so we're going to look at the difference between the two. Now what cyclohexanes can do is they can do what's called a ring flip, okay? And when you do that, all the carbons kind of flip places, and your substituents flip from what was axial becomes equatorial, what was equatorial becomes axial, okay? And so we're going to flip this ring and kind of draw its like matching left or right hand. And so again, when you're drawing it, you want to think about that series of parallel lines. And a lot of times when you get to draw these, you become good at drawing it one direction, but it becomes a little bit more difficult to draw it the other direction. So we've got parallel lines here, parallel lines here, parallel lines here. This guy's still a little bit too much of a right angle there. And so now, this point is this point, and this point is this point, okay? And so what was on top, equatorial, is now axial. Here, these become equatorial instead of axial. Then it drops down behind to be axial, equatorial, then axial, and then here, these guys become our axial. And we can draw this one going up in front of that ring, like that, okay? And so all these could be hydrogens, or they could be other things on that cyclohexane ring, but we're going to practice going back and forth between our different forms of the chair, and what happens when things are axial, what does that do to the energy versus what happens when they are equatorial, okay? So you'll get lots of practice with these guys this week. Now for lab, you're going to need to bring some things that are a little bit different than usual. You're going to want pencils for filling out. You're going to fill out the answer sheets eventually that are in your lab manual. So I bring pencils in case you need to change things, just like I was erasing, and erasers. And even note paper would be helpful too, in case you don't want to put your answers into the answer sheets quite yet. So bring definitely pencils, definitely erasers. If you have a laptop, bring it with you, because you can use your laptop to do this experiment. So if you have one, go ahead and bring it with you, and we'll help you in using it. Otherwise, we'll also use computer labs too. Bring your McMurray with you. There's a couple problems from this week's experiment that actually comes directly out of the problems at the back of the chapters, so bring that with you. If you have any physical models, bring those with you. Otherwise, we'll have some for you to check out during the lab period and then return. So your pre-lab, there's nothing that's going to go in your lab notebook, okay? So this is your 1 week off. Everything's going to go on those answer sheets. But you want to review Chapter 2 in McMurray. So this is your pre-lab. Instead of writing it out, you're going to review Chapter 2 in McMurray. And you want to look at Figure 2.3 and Sections 2.3 and 2.4. Then you want to review Chapters 3 and 4. And you want to look at the structures in stereochemistry. Of alkanes and cycloalkanes. Okay. So questions at all with any of this? Good? Okay. What I'm going to do now is actually demo some of the basics of using WebMO so you're familiar with it, so when you come to lab this week, you can jump right into the experiment. What we're going to be looking at are pages 2.2 and 2.3 for the demo. And I'd like you guys to see. Okay. So you can access what we're going to use for WebMO anywhere on campus that you can get into the campus server. Okay? So you're going to use curie.chem, like Madam Curie, curie.chem.hope.edu, and you can get into the server. With that, you can also use Chrome, you can use Firefox, you can use Internet Explorer. All of those will work. Some of them vary how well they work on one computer versus the other, but try and use the newest versions of those. So especially in using your computer, if you have one that's newer than the other, then I'd probably use that. I'm going to use today, I'm using Chrome because it seems to have the most hurdles you have to jump through in using it, and most times that it asks you, is it okay if you do this or that or that kind of thing, okay? So that's what I'm going to be demoing with, but Firefox and Explorer will work as well. So once you use curie.chem.hope.edu, you're going to go down on the left-hand side. You're going to click on WebMO, and then you're going to click on Organic Chemistry, okay? And I'm going to have someone else demo the sign-in for me because I've already signed into WebMO, so it knows who I am. Your username is your Hope username without @hope.edu, and your password is your email password as well, okay? Then once you put that information in, it's going to ask you for your lab section. You only get asked that once, so you want to make sure the first time you put it in correctly, okay? So I'm going to have, you want to come up?
So, like that?
Mm-hmm.
And the password is just
Whatever.
email password?
Yep. And then you would select your lab section, and then there's no group password, so then you just say login.
There we go.
Okay. And now what I'll do is I'm going to log out it so I don't put a bunch of jobs in yours
Cool.
and put in mine. Okay? So that's all you need to do for logging in. Just remember, select your lab section correctly, because we can go in, your instructor can go in and look at the jobs you have done. And so you want to make sure that everything's correct so that you can we can look at those things for you. So now I'm going to go through and show you how to use a couple of the functions of the WebMO and do some of the more complex calculations. And so like I said, I'm following the instructions on page 2-2 and 2-3, although I'm not going to necessarily point at each instruction. So first thing is we're going to go to New Job, and we're going to create a new job. And one thing with using WebMO, you want to make sure you have the newest version of Java on your computer. It uses Java a lot. And it also will keep asking you if it's okay if it uses Java. So you're just going to say run, or yes, or okay. It never quite asks you the same way all the time, but you just keep saying yes, or okay, or run. So what I'm going to start with is we're going to draw propane. And I'm going to show you some of the calculations we can do on this screen, and then we'll go on to the more complex calculations. So this guy here is our build molecule tool, and it defaults to everything being carbon, okay, which is fine for propane because we've got 3 carbons in there. So you're going to right-click on the screen, you'll get a carbon, and then click on it and hold down, left mouse click, and then release, and then you can get another carbon bonded to it, and then again hold down and release, and you'll get the 3rd carbon. Okay, so we've got the carbon backbone of propane. If we wanted something else besides carbon, then click on the periodic table looking tool, and then you have access to everything in the periodic table. Okay, so you're not just stuck with carbon. For most of these, all you need to do is draw the carbon backbone, unless the backbone is something else. And then you're just going to click this comprehensive cleanup using mechanics, or this wrench, and that will add the protons for you. Okay? And we can use this tool at the very top, this arrow. If you click on that, then you can hold down left mouse button and rotate all around to show all of propane and its structure. Okay? And you can look, like if we wanted to look down, carbon 1, carbon 2, then we'd see the methyl group alphabet, so on and so forth. Now, a couple of the calculations you're going to need to make are bond angles and bond lengths. So to do that, what you want to do is rotate the molecule around so you can see what angle and what length you want to calculate. And then you're going to click this tool here. This is called the Adjust tool. You'll just click it, and then you select the first atom that you want as part of your bond angle or bond length, and then you hold down the shift key to select the rest. So if we want a bond length, we could just, this proton and this carbon, and then we've got the bond length down here in the bottom. If we wanted an angle, we could select another carbon. We've got the bond angle down here. Or if we wanted the dihedral angle, which is the angle between 4 atoms, then we could click this guy, and then we've got our dihedral angle. Okay? So those are three calculations that you're going to need to do and write things down for that. Okay? Now with our propane, we could go on and do more advanced calculations, and so to do that, we're going to click on this arrow in the lower right-hand corner, and we're going to say yes to following the application, and we're going to continue without symmetrization. And for this first calculation, we're going to click on Tinker, and then select this arrow. And then we want a molecular energy calculation, and we want the force field to be MM3. Actually, sorry, we want geometry optimization and then MM3. So then we click this here, and this basically, that arrow then puts it out to actually have the calculation run. Okay? And so the job manager refreshes every once in a while, or you can hit the refresh button, and hopefully it goes from queued to then complete. And some of the jobs take longer, the more complex jobs, some of the jobs are done sooner. So then you click on your job name, and I've named mine all by default is molecular formula, although you will probably want to use your initials and then what you are drawing. So, you know, ABJ ethane, ABJ ethylene, whatever that is. So that when your instructor looks at the whole class of all the jobs, then they can find the ones that are associated with you. Okay? So we'll click on the job name. And for this one, what we are looking at, we can first of all, we could rotate molecule and look at it and look at how much it has changed in just doing a more complex calculation to get the energy minimum. And then we can look down here, we had our geometry optimization calculation performed, and from that we can get the total potential energy. And so for that part of the experiment, you'd scroll down below this screen to get the total potential energy. Okay? So now let's work with something else. So we're done using propane, so when you go back, yeah?
Can you like set it up to show the energy maximum?
Eventually, yes, we'll get to that with one of them. So you'll see it in multiple ways. You'll see it as a map, and you also can click on minima and maxima to see it. So I'm not going to show that today, but one of the ones that you work through during the lab, you'll do that. So now I went back to the job manager. We're going to create another new job. This time I want to get to where I show you an electrostatic potential map. And so to do that, we need to use something that, better than propane, is going to have differences in the electrostatic potential. Okay? And so what I'm going to draw is chloromethane. So I've got my carbon here. Then I'm going to go into the periodic table and select chlorine and add that guy, and then do the wrench again. And so now I've got my chloromethane. I could go through and do the calculations here with the adjust button. I could do the bond length. I could do bond angle. We don't have enough atoms here that we could do dihedral angle. But what I'm going to do now is go on so we can calculate the electrostatic potential. So I'm going to click this arrow on the bottom and then say OK. Then I'm going to click, this time we're going to use the MOPAC engine for the calculation. And we'll click this arrow. And we're going to calculate the molecular orbitals. So we'll select that, and we want PM3, and then the rest of this is what we want. So just make sure as you're reading through each of these steps that everything is selected that you want. and then hit continue. And so this one's going to take a little bit longer, but not too long. So once I hit refresh, then it was ready to go again. So I'll select it. And now we're going to we've got more things going on with this calculation. So we'll say run. So we've got, again, our chloromethane that we can look at, and it's been optimized. But now we're going to scroll down below the molecule itself, down to where it says molecular orbitals, because that's the calculation that we had to do. And we're going to click on electrostatic potential and the magnifying glass associated with electrostatic potential. And we'll say yes. And so then we get the electrostatic potential map for the chloromethane. Okay? And in order to make it so that you can see the compound, sometimes it's bigger than the screen. You can click in the screen, and then you can use the mouse wheel to make it bigger or smaller. And then just hold down the left mouse button to rotate it around. And then you can click on this icon here, and we can actually change how opaque or not the electrostatic potential map is. So if we go from 100% to somewhere in the 60s and say apply, and then okay, then you can actually see the compound underneath along with the colors that are associated with it. Okay, so you want to do that for the questions where you're looking at electrostatic potential, so that you can see what is associated to with the different colors of the map. So up here at that chlorine, what kind of electron density do we have? High electron density. Does that make sense? Yeah, because it's a more electronegative atom, versus down here with our carbon and hydrogen, we're down into the blue, so that's a little more electron poor. Okay. Now another part of what you're going to have to do, so we're going to go back to the job manager, and we'll go to a new job, is you're going to have to look at cyclohexane and the conformations of cyclohexane. Okay. And so to find the cyclohexane, what you want to do is go under build, and under fragments, you're going to look for rings under functional groups, and then what type of ring, and you'll select either the chair, the boat, the half chair, or the twist boat. Okay? So when we're looking at different energies, select the right thing. It'll tell you which fragment to select. Okay? When you are building cyclohexanes to look at different substituents, you're always going to select the chair. Okay? But at first, before you do that, you're going to look at the different conformations and figure out what the energies are of each conformation. Okay, so if we select the chair and say OK, then come down into our screen here and left mouse click, then we'll get the cyclohexane ring. Okay, and then you can rotate around and you can look at it as a chair. Okay. If you minimize this guy, then you can get the energy for that chair conformation. Okay. What you want to do, though, is make sure, so let's go to a new one, make sure you minimize only what it tells you to minimize, and not every time you put one of the fragments in there. Okay. So if you want to look at the twist boat, actually, let's look at the boat. Okay, so our boat conformation looks like this, okay? For those of you who have gotten to look at conformations of cyclohexane, is the boat a maximum or a minimum?
More of a maximum?
to maximum, right? So if you want to look at the boat's energy, if you click the wrench, you'll actually end up with the twist boat, okay? So see how it's now different than it was before, okay? So don't, when you kind of look at it this way, you don't want to click on something and minimize it when you don't want it, and it's like kind of like a partial twist boat here. If you don't have to. So some of the fragments it's going to tell you to minimize it to get the energy. Some of the fragments it's going to give you the energy on the worksheet. So just use the energy that it gives you. Okay. So let's go with a new guy here. The other thing you're going to do is for the last two problems that you're using the computer program, using WebMO for, you're going to actually need to copy and paste what you made in WebMO and put it into a Word document and print it out, okay? And so, let's go back to, we'll make a cyclohexane here. So we've got our cyclohexane. Say, this isn't one of what you're going to be printing out, but well, let's make it a methyl cyclohexane and get the energy. And we'll kind of try and, what you want to do before you copy and paste into Word is have it take up as much space as it can in the screen, in your build molecule area, and then also rotate it around so that you can see everything involved. So when you print it out, we can see everything that you were able to see, okay? So something like this would be better than something like this where things are overlapping and we can't see everything, okay? So get it rotated just right so we can see what's going on. And then what you're going to want to do is use Alt. Open up Word so it can be opening while we're doing this. What you're going to want to use is Alt or Function, and then the print screen button on the upper right of your computer, and then go to Word and do Control V. So you're basically copying and pasting that screen into Word, okay? And so then we have the molecule, and then what you can do for the molecules that you're going to put into Word, you could then either above or below type the energy that you were calculating for it, okay? And for menthol, you're going to be looking at two different conformations. Then the other one is for morphine, so you're going to just have one compound, but it's a lot more complex that you're going to do this for. So it's instructions 27 and 28. But when you go to hand in your worksheets, don't forget that you need to print these guys off too. Okay? So for experiment 2, what you're going to hand in are the answer sheets that are at the end of experiment 2, and then these 2 printouts, and they're due 2 weeks from your lab period this week. Okay? So they won't be due next week, but they'll be due 2 weeks from now. All right? Questions you guys have?